Kamali has been staring at her textbooks for 6 hours straight. She's memorizing formulas, sketching out complex diagrams, and her brain is absolutely fried from the effort. Or take this person, putting every ounce of their physical strength into pushing a massive, immovable rock. They are sweating, their muscles are burning, and they are on the verge of total collapse. Then there's a third person, standing perfectly still while balancing a heavy crate on their head. Their legs are physically shaking under the sheer weight. In our everyday language, all three of these people are working incredibly hard. But according to the strict laws of physics, zero work has actually occurred. Our colloquial definition of work is tied to our biology. We measure effort by how exhausted we feel, how much we sweat, and how many calories we burn. But the universe doesn't care about our internal energy drain. To understand the mechanics of reality, we must let go of our emotional perception of effort. We have to learn the strict, mathematical language that governs how physical objects actually interact. In physics, for work to happen, two non-negotiable conditions must be met. First, a force has to be applied to an object. You have to actively push or pull on something. Second, and this is the catch, the object must actually move from its original position. It has to be displaced. The core equation, work equals force times displacement. Applying massive force with zero displacement means multiplying by zero. Total work is zero. Work also has directional polarity. Force aligning with movement is positive work, but gravity pulling down against an upward lift is negative work. Work, therefore, is the successful directional movement of matter against physical resistance. So if work is the act of moving things, how do objects acquire the ability to exert that force in the first place? They need energy. Energy is essentially the universal currency required to perform work. We measure this capacity in joules, named here after the 19th century British physicist James Prescott Joule, who verified that energy could change forms. One of the most obvious forms this takes is kinetic energy. This is the energy an object possesses simply because it is in physical motion. A heavy stone rolling across a flat surface can smash into a target and do physical work, completely due to its momentum. As we see in this formula, an object's kinetic energy is equal to 1/2 of its mass times its velocity squared. Because velocity is squared, the math dictates that if you double the speed of an object, its kinetic energy, its constructive capability, quadruples. But an object doesn't have to be moving to hold energy. It can also hoard it in reserve. We call this potential energy, and it is stored strictly through an object's physical configuration or position. Look at this stretched metal slinky. By winding a toy or pulling a spring, you are doing work on it. That effort doesn't disappear. It gets stored inside the metal as mechanical tension, ready to snap back and do work the moment it's released. You can also store energy just by fighting gravity. When you lift a textbook off the floor and hold it in the air, you are actively packing it with gravitational potential energy, calculated by multiplying its mass, the pull of gravity, and its altitude. An object only gains the ability to change its environment, to do actual physical work, by storing energy in its motion, its physical shape, or its altitude. All of these energy transfers are governed by a strict cosmic rule, the law of conservation of energy. Energy can never be created out of nothing, and it can never be destroyed. This diagram illustrates the rule. Here, potential energy is at absolute maximum, and kinetic is zero. As the sphere drops, potential energy drains, converting precisely into speed, filling the kinetic bar. At the bottom, kinetic energy reaches maximum. The total mechanical energy always remains constant. The total mechanical energy in a closed system remains perfectly constant. The universe operates a perfectly balanced ledger. The energy simply changes costumes. While the universe's energy ledger always balances out, human reality cares about one final variable: time. Specifically, how fast the work actually gets done. Imagine two identical machines lifting the exact same weight to the exact same height. They both do the exact same amount of total physical work. But if one machine finishes the job in half the time, it is objectively more capable. This is power, the rate of doing work. It's calculated by dividing work by time. Notice the math. When the time variable shrinks, the power output automatically scales up. High power simply means you are transferring energy at a much more aggressive speed. Which brings us back to our exhausted student and our friend sweating against the immovable rock. They are certainly expending biological energy, but true physical work is not a badge of human suffering or fatigue. It is the mathematically precise mechanism by which the universe moves, alters, and continuously passes its eternal currency of energy.